Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended discussion on identifying potential root causes for eventually building a data collection plan, or DCP. In this lesson, I'll specifically be reviewing the cause and effect diagram, or C&E diagram, and how that can be used for building the DCP. So it's essential that you at least review the previous lesson that I've talked about in introducing the DCP.
Well, a measurement system refers to the method that's used for collecting data or actually calculating the metrics. And here's some examples of some measurement systems. Churn is one. If you have a subscription-based type of revenue for the organization, you can calculate that by saying it's the number of customer cancellations divided by the total number of subscribed customers, if that's the type of revenue that you have. Or another metric is OIBDA. There's several variations of this, but the common one is it stands for operating income before depreciation and amortization. And the calculation for that is taking your operating income and adding into it depreciation, the amortization, tax, and interest as well. Also, another one is ARPU, also stands for average revenue per unit, which is basically taking your total amount of revenue and dividing it by the total number of units. Now, a unit could be the number of customers that you have, number of products you use, depending on however you want to divide into that type of unit for your type of business. Also, another one is for like a call center, you might have average call duration, or sometimes called average handle time, where you're taking the total call duration, whether that be in seconds or minutes or however your organization tends to calculate that, and divide that by the total call volume that that organization handles. These are just a few examples of the types of metrics or measurement systems that might exist within your organization. But how do you know that you can trust whatever measurement system you might have? There are many metrics that are out there, and sometimes we take those for granted. But how do we know that they're accurate and that we can trust them? What's the risk of having errors in the measurement system? And what if there is no measurement system that exists for what it is that you need to measure? Then how do you create a measurement system? Well, this is all part of what we need to explore. We need to understand that a little bit further, and the measurement system analysis, or MSA, is one way to do that. Well, a measurement system analysis, or MSA, is a method that's used for testing and validating the accuracy and precision of the measurement system. It measures the level of risk that you might have in the reliability or the validation of that measurement system. It's not just a matter of doing calibration. It's more of a formal method that's used, or methodical process that's used for analyzing that measurement system. So when we say accuracy or precision of the measurement system for what an MSA tests, then what's the difference between accuracy and precision? Well, accuracy refers to the measurement of how correct a measurement is, that is, to some sort of known standard or some master that's already predefined. Precision refers to the amount of variation that's within the same operators that are doing the measurement, or between different operators. So again, it's looking at precision between them. Now, just to illustrate a little bit further, we might say here's an example where when you're throwing darts at this dartboard, this is accurate because every dart had hit the dartboard, but it's not very precise because it's pretty scattered. However, here's an example of where none of them hit the dartboards, but they are pretty consistent in where they hit. So in this case, it's very precise, but not accurate because it didn't hit the dartboard at all. But if you have something that is accurate and precise, then you're consistently hitting it in the exact same spot and hitting the target that you're trying to define. Again, this is just an illustration to show how we might explore accuracy versus precision. We're going to explore that a little bit further here. When we talk about measuring accuracy and precision in an MSA, what we're really referring to is looking at the accuracy and precision from three different perspectives. First of all, from an accuracy perspective, well, it's pretty straightforward to say that we're looking at the accuracy of the data. Is the data recorded correctly, or is there any bias that's within the data? But from a precision perspective, we're actually going to explore that from two different perspectives. First of all, repeatability. Is the data recorded consistently by each operator or within the performance of each operator? Versus reproducibility, which is the data recorded consistently between different operators. So one is looking at the performance within the operator, the other one is looking at the performance between two or more operators. Now, it might be confusing in order to remember the difference between repeatability and reproducibility. One way to remember it is that it takes two people to reproduce. Well, in that way, reproducibility is referring to when there's multiple people involved and you're doing the comparison between different operators. Now, there are some additional perspectives that could be applied when looking at the MSA and doing analysis on it. One is linearity, that is there bias over the operating range. Another one is stability, is there variation over time in the data process or within that measurement. measurement system. And then finally also resolution or discrimination, which would ask, is the measure granular enough, or is it low enough scale scrutiny in order to detect small bias or variation? Well, these are some additional perspectives, but actually for the exercise that we're going to be looking at and exploring the MSA, we're going to limit it to just looking at these other three perspectives of accuracy, repeatability, and reproducibility.
Lesson, I'll specifically be reviewing the 5 whys concept and how it could be used for building the DCP. So it's essential that you at least review the previous lessons leading.
Well, what I'll illustrate now is an overview of how the flow of an MSA might typically work, looking at those three perspectives of accuracy, repeatability, and reproducibility. And the example I'll show you now, it's going to be as if there were 3 different operators that are going to be doing 3 separate review trials of the same types of items that are being reviewed. So in this particular example, let's say your measurement system is something where you have some people, some regular operators, who are actually tracking something either on tick sheets or they're recording some data for you based off of something that you're trying to measure that may not already be recorded in the system. So what you want to do is you want to make sure, are these people recording it correctly? Because if you're relying on this data that they're recording, how do you know you can really trust it? Well, if you want to be able to assess that, how well you can trust the process that these different operators are using to record this data, and you want to trust it, again, their accuracy and how repeatable they are within their own process, as well as the reproducibility across the multiple operators, this is one of those examples of how you can do that. So let's just say you've got a certain set of items you've predefined that you want to review. And with that, you're using that as a basis to define the master, the actual output or that standard that you're using that you want to see as the results from the different operators. So you've got 3 separate operators that you're working with, and you want to be able to run this test with them. These are the folks that are recording the data for you, and again, you want to assess, can you trust the data that they're recording? Well, we've got a first review trial. You're basically getting one set of data that you're providing for them, of telling them this is what you want them to record for you, either from the system or through some transactions or however it is you're processing it. You've defined up front the first set of items you want them to review for you. Well, you send those items to each of the operators. You're sending the same set of items to them. And by sending it to each one of those operators, they create some sort of output, whatever it is, the result that you're looking for from them. Then you also set up a second review trial. And in this example, we could say maybe it's the same exact data that you want them to look up, but you don't tell them it's the same data, because maybe that's possible where they may not realize they're looking at the same thing. Well, if you got a second review trial like that, again, you send it to each of those operators, and then they create some additional output based off of what you sent them. And then you might have a third review trial with them. You're sending that third review to each of them, and again, they're outputting a third set of items for you. Now, at the end result here, what you have are 9 separate items, 3 from each of these operators, and what you want to do is compare each of those items to the master. By comparing it to the master to see how close they are from an accuracy standpoint, that tells you, again, how accurate they are in their process of recording this data. Now, if you want to compare within the performance of each operator, how are they at following their own process and recording the same data? That's testing for repeatability. Again, comparing the output within the same operator. Reproducibility is looking at when you're comparing that output data across the other operators and the outputs that they had. That's doing the comparison between operators. So here's where we account for the accuracy, repeatability, and reproducibility. Now, in this example, it represents a blind study. That is where the operators don't necessarily know that they're processing the same information. That way you have one master that you're comparing it to, and all these reflect the same ideal output you want them to have. Now, if you can do it, that would be ideal. But the example could be something that you want to use in a transactional type of environment where maybe the operators themselves don't realize, again, that they're working with the same data. So it's really helpful if you have that kind of environment where that can work. So transactions that they could review could be things like calls from customers or invoices or purchases or some other transactional based information from the system that they might be recording. Now, in the manufacturing environment, though, what they might be looking at is a part or a product, something that they're reviewing to test for number of defects or certain quality assessment within the parts or products or whatever is being reviewed. Again, it might be more difficult in that type of environment if you pass the same thing to all of them. If you already know a level of defects within the parts you want them to examine, it could be difficult because they might see that this is the exact same part that they've examined before. So it might be more difficult to do a blind study in that type of manufacturing environment. But when you you have a whole lot of transactions that are being processed, and if you send them in a different order and randomly in a different order for each of the operators, they may not even realize they're actually processing the same type of information. Again, what you want to do is you want to make it as random as possible, and you don't want them to be aware, if possible, of what they're analyzing, because you don't want to introduce any bias into the process. And if you have that opportunity to do that, that would be ideal, and that would be like the blind study. But if you can't, well, then it is what it is. You can try to do the best you can, but you might find yourself using multiple masters or references to compare the accuracy to if you happen to have different sets of items that you're having them review.
Now, it can be used for building the DCP. So it's essential that you at least review the previous lessons that first introduce you to the DCP and the C&E diagram.
Let me explain a little bit further what I mean. An MSA can get very complex and take extra time, as you can see from that previous example I showed you. Now, the more complex that you have an MSA, that is, if you have a lot more variables that are involved, or if it's more operator dependent, that is, where you have a lot of manual processes that are involved and a lot of measurements, things that they're recording. If you have a lot of things like that in your measurement system that you're trying to assess, then it's going to require a lot more time in order to conduct the MSA. So if it takes so much time, then is an MSA really necessary? Well, maybe. The short answer might be no, but there's some things you need to consider. Like everything else, it really depends on risk. That is, what's the risk of not doing an MSA? Well, how are we going to measure something like that? How do we measure the risk of not doing an MSA? We can't really measure that. There isn't a formal or objective way to measure the risk of not doing an MSA, but there are some ways that we can subjectively assess the risk by asking ourselves a few questions. For example, are you at least 90% confident that you can trust the accuracy of the measurement system? Are you at least 90% confident that you can trust the precision or lack of variation of that measurement system? Is the measurement system not based on human involvement? That is, it does not involve time and motion studies or tick sheets or some sort of manual recording of the data for the measurement system? Is the speed of finishing the project more important than the accuracy or the quality of the analysis? And that's where you get into the balance of comparing risk versus reward, like we've talked about in previous lessons. If you later discover the data was unreliable, then would it be acceptable to just go back and recollect the data and do the MSA later on? Well, if you can at least answer yes to these questions, then it may be appropriate to skip the MSA after all. Now, if you're going to skip the MSA, though, or if that's what you want to do, then you should at least carefully review those answers with the champion and sponsor so that they're at least aware of the risks if they decide they want to skip the MSA. Again, if you cannot answer yes to these questions that are asked on here, chances are there is some risk that you're exposing yourself to if you do not conduct the MSA. And it may be worth the work, because after all, if you find later on, after doing the MSA, that there was some critical error in how the data was collected, and you can't trust the reliability of the data, then any further analysis you do on the data is not going to be reliable as well. So it's absolutely essential that you have data that you can trust. If the MSA is the best way to do that, then it might be absolutely necessary to do the MSA. Again, let these questions that are asked in here be a guide for you to tell whether you should conduct the MSA or not. Now, since MSAs can take on many different forms and can get very complex, what we want to do is go through a simple process about that. So the module we're looking at right now is going to introduce some of the concepts for using a simple set of MSA tools that are most common. Again, it's not going to get so complex getting into the other perspectives that we introduced before, but we are going to go over the fundamental concepts and exploring how you can conduct an MSA. The four general steps that we're going to use for building the MSA begin with planning the MSA. That usually involves determining what needs to be measured, what MSA tools are going to be used during the MSA, and who's going to be part of the study itself, what samples or masters are we going to use for testing the accuracy, and how are we going to conduct the actual study itself. The next step is to actually conduct the MSA. That's going to involve scheduling the study, leading the study itself, and actually running it, and then collecting the data from the study. Once we've done that, then we can begin the third step of analyzing the results from that study. That's going to involve compiling all the data that was collected during the study, processing the data using the MSA tools that we plan to use ahead of time, and interpreting the results and doing the analysis on that data during the MSA. And then finally, after we've done that, we want to improve the measurement system. That's going to involve determining if we need to make improvements to the measurement system itself. If it does, then we need to find out what are those improvements and changes we need to make to the measurement system. And if we're making changes to the measurement system because we didn't trust reliability before and it failed the MSA, then that means we might have to redo the MSA. And when we redo it, that's a way for us to assess whether the corrections and changes we made to the measurement system were effective enough to the point where now we can trust the results coming out of the measurement system.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to think of at least 3 projects or initiatives that you worked on in your organization in the past. And for each of those, I want you to ask yourself a few questions. First of all, at any point, was there any data or critical information that was accused of being unreliable within any one of those projects? And if there was, then what caused the accusation to be raised? Was the accusation actually true? That is, was it true that the data really was unreliable after all? If it was true, then why wasn't the reliability of the data tested ahead of time? And how could an MSA have helped catch or prevent the unreliability that was found in the data? Otherwise, if the data was reliable after all, despite the accusation, then what could have been done differently to have prevented that accusation in the first place? Now, if there was no such accusation at all, then why not? That is, what kept anyone from actually challenging the data, challenging the reliability of that data? Should the data have been challenged, but perhaps no one was willing, or maybe they weren't knowledgeable enough to even challenge it in the first place?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.